As information professionals, we're always concerned with databases. Shoving data in, yanking information out. Databases are our business. There are two major kinds of databases. Flat files, which we're all familiar with, and relational databases, which are more complicated. Flat files work the way they look. They're a big old file with a number of fields in a set order, generally with one record per line. Excel spreadsheets are a good example of this sort of thing. They're great big slabs of data. Relational databases break that great big data table into a bunch of little tables, each representing a separate piece of data. In this example, we have one table for books, one for authors, one for publishers, all busted up and only brought together when they're queried. It may look complicated, but don't worry. It is. Flat files are intuitive. What you see is what you get, but they have some limitations. Flat files are simple, and if your data stays simple, they might be the right solution. But data doesn't always stay simple, and sometimes your data structure doesn't fit your data. Modifying a flat file's data structure to match new forms of data can make for real ugly databases. Here, adding fields for special cases means tons of empty fields in our records. In a big database, that can cause problems, as well as wasting space. A well-made relational database can fix a lot of these issues. A relational database doesn't grab all of its data from just one big table. It grabs it from multiple places. This example table can be split up into these 4 tables. And now you might be asking, why? It looks ugly. It's not intuitive. You're going to be trusting your software to do a lot of that work. But there are distinct advantages to using a relational database. One is greater data integrity. In a proper relational database, all data is put in only one place, and all queries and records that use that data get it from that same place. So if you need to update or correct some data, you need to do it only once, in only one place, and every record that references that data is automatically updated. This also means that the database has less duplicate data. In a flat file, even one that's been properly made, you can end up entering the same data again and again and again. If it needs to be changed, then it needs to be changed in multiple places. In a relational database, you enter something once, and if you need that data elsewhere, you reference it. A good relational database can also reduce query bias. A flat file's design can tend to make it easier to do some queries and not others. Since a relational database has more access points and no real hierarchical structure, it's open to more sorts of queries. The last big advantage is greater data normalization. This is a pretty complex topic, but the simple way of thinking about this is, blank fields might not kill your database, but they will make it harder to read and harder to use consistently. Normalized data means that if your information item doesn't use that field, there won't be an entry in the database for it. No special cases, no blank fields. It's more of a goal than a reality, but relational databases make it much more achievable. Look at this nice report. It's simple, and sure, it could have been done from a flat file, but this was built from information in 4 different tables: an author table, a book table, a publisher table, and a relationship table that helped connect all the records together. The work of putting this report together would have been done in software, not by hand, but to design the database, we need to know what information we want to get out of it first. The bulk of the work for a relational database is done up front. In this simple flat file, we have the basic idea: titles, authors, ISBN, and publishers. How are we going to break that up? First, we look at the items and their relationships. Books need a table, but what goes in it? Well, a book has title, author, number, and publishers. But look at how many it has. A book will have one title, one ISBN number, and one publisher. But one publisher can have many books, and one book can have many authors. So we know books need their own table, but publishers need one, and authors do too. See, the book table has titles because a book has one and only one title. That's a one-to-one relationship. It also has an ISBN number, which is a one-to-one relationship. There aren't going to be multiple books with one ISBN number. Now, a book has one publisher, but a publisher will have more than one book. That's a many-to-one relationship. We can have the publisher in the book table, but since we're going to be using that publisher data again and again and again, it should be in its own table. Books also have authors, sometimes more than one, and authors write books, and again, often more than one. That is what's called a many-to-many relationship. You can't put that data in the book table or in the author table without screwing up your data normalization. So you need a fourth table that will connect the two. This table contains only references to authors and books, bringing them together. If an author like Neil Gaiman or John Connolly has written several books, they will have several entries referencing their author record, and then the books they have written. For Footfall, written by Jerry Pournelle and Larry Niven, each author gets a reference to a single book. No information is repeated. No fields are left blank. It's complex and difficult, but also kind of elegant. One thing to note is it's unlikely anyone will do any of this by hand. Using relational database management systems like Microsoft Access or MySQL is much more likely. The power of the system is in the queries you can make and the ways you can manipulate this separate but related data. The system, of course, will have its problems. If you delete a record in a flat file, it's gone, and the file lives on undisturbed. In a relational database, other data will likely be referencing the record you just destroyed. This can be bad if the software isn't robust enough to handle it. But in a well-made database, a lot of these relationships will be transparent. But since we're information scientists, we need to know how our data is working, not just that it does. I hope this helped you get a little bit of an idea how a relational database might work. Thanks for your time.